Good afternoon, ladies and gentlemen. I am very pleased to present you this opportunity to do a national project. The current challenge for construction is to satisfy, on one side, the growing demand in building and infrastructure, while achieving simultaneously a massive global reduction in greenhouse gas emissions. To succeed this challenge, I fear that the easy solutions have already been implemented. And my opinion is to go further and further toward sober design will require much deeper knowledge and a huge general improvement of the technical and the scientific level of all the players in the sectors. Each player has his own responsibility in this and also has his own duty in this success. The owner, the designer, the contractor, the insurer, the regulator, the stakeholders, the researchers, and even the lawyers. As a contractor, the choice to build a structure at a given place for a given purpose is not under my control. It's the owner's responsibility. As a designer, as a contractor, the greenhouse gas emission of 1 ton of cement or of 1 ton of rebar is not under my control. It is the manufacturer responsibility under the state of the art. But as a contractor, I am liable for the emission linked to the scope 1 and the scope 2 of my activity. Thus, I shall do my best to reduce these scopes and improve my processes. But unfortunately, the scope 1 and 2 represent merely 1/10 of the emission linked to scope 3. And thus, it is scope 3, the global emission linked to scope 3 are the emission linked to the materials included in the structure and linked to the future use of the structure. But fortunately, as a contractor, I can use my weight, my expertise, and my will to minimize as much as I can the scope 3. And among many strong passes, there are 3 particular ones. Minimization of concrete emission through the choice of adequate concrete mix. This path is not the purpose of this lecture. The minimization of the amount of reinforcement placed in the concrete. French contractors are responsible of the design, so we can do it, help it. And also increase the lifespan of the structure for the same resource and the same emission investment. These 2 last paths are the purpose of this lecture. Up. So, let's have a look at some findings. This last decade, standard evolution, and in particular Eurocode and 5 model code, aim to provide, on one side, a better safety by a better account of the loading reality, and also a better achievement of the structural durability. And this has been obtained through concrete mix design improvement, through minimum cover, and also through explicit limitation of crack width. And as a consequence, for several types of structure, this evolution leads to a very important increase of the ratio of steel in reinforced concrete. Just have a look and compare the old French BAEL standard in prejudicial environment with the C2 Eurocode standard in XS1 environment. For building, it's more or less the same. But if the structure becomes a little bit massive, if you use high performance concrete, if you use large rebar diameter, and if you use large cover, the difference becomes enormous. This picture is provocative, but somewhere with high performance concrete, you have a low binder, water binder ratio, so you obtain a sticky and viscous concrete. And due to the fact that the ratio of reinforcement increases, you obtain a very dense reinforcement. So the mere error during the placement leads to catastrophic situation where obviously, which obviously they jeopardize the initial objective. Also, there are tricky issues with the crack width limitation approach. Current principle for durability, rebar durability in concrete is more or less the following. First, we suppose the concrete uncracked. And then we estimate the penetration of the kinetic of the penetration of aggressive product in the concrete. And somewhere the lifetime is reached when the aggressive agent reaches the rebar. This approach leads engineer, designer, controller to think that end of lifetime more or less equivalent to beginning of corrosion. But reinforced concrete, by essence, is cracked. And in a crack, the corrosion starts immediately. Not immediately in terms of seconds, or in terms of hours, or days, or weeks, but immediately regarding the lifespan of the structure. So there is an apparent contradiction. And this contradiction is solved by saying, if your design crack is lower than a given value, everything happens as if the concrete were uncracked. But is it true? Other tricky issue that national annex are changing. For example, in Netherlands in 2011, for XS2 exposure, the admissible opening changed from 0.3 millimeter for quasi-permanent load to 0.2 for frequent load. That means more than 50% more reinforcement. Why? 5 years later, Netherlands introduced a multiplying factor, coefficient, KC, to be applied on the admissible crack width. The idea is the following. You have here reinforcement and the crack with a shape with a which diminish with the thickness. Here you have the nominal minimum durability cover, and what you want is to have WK at this location. So you admit for the nominal cover a higher opening. So somewhere in 2011, you increase the amount of reinforcement, and in 2016, you decrease the amount of reinforcement. Many countries, such as Norway and UK, did the same. Now, the link between crack width, calculated crack width, and in situ crack width is more or less tenuous. And also, it is very difficult to measure. Why? Because first, there are no standards to measure the crack in situ, which is a subjective measure, which depends on the mindset of the guy who takes the measure. It's sensitive to the measuring equipment. It's not easy to do. And in fact, is it useful? But the problem is that with a contract, with the client, if you have large cracks, your structure is bad. You work badly. It's a problem. Even in laboratories, the link is tenuous. This is some results of last national project called COS.fr with large samples, 800 millimeter fixed, 1.6 meter wide in flexural crack. And on one sample, on two nautical samples, on one, all the cracks were above the calculation, and the other one, all the cracks were below. And also, we can ask with this kind of crack pattern, if the surface crack is really pertinent. But the biggest problem is that the designer and the owners believe less and less in the ability of the concrete to provide a protection during the lifetime of the structure to the reinforcement. So they ask for cathodic protection, for example, in Nouvelle Route du Littoral in La Réunion. They ask for stainless steel rebar, or even stainless steel tendons, or even carbon fiber reinforced rebar, for example, in Florida. Or they ask to paint the structure, like in Gulf or in petroleum industry. Or sometimes you have to add some various compound, like a crystalline compound or poudre of perlimpinpin. And this is without relaxing the other criteria. So you have to put the large cover, you have to limit the crack width, you have to have very, very high performance concrete, plus cathodic protection, plus. And the question, is it reasonable regarding the need to reduce the environmental impact of structure? So this leads to a question, and this question is, does crack width limitation is necessary? There are questionings about that. But also the question is it sufficient? Because probably not necessary in many cases and probably not sufficient in other cases. So the question is, what are the effects on the initiation of the propagation kinetic of corrosion of, for example, lots of phenomena, the crack orientation, the crack origin, the crack position above or below, the quality of the interface. We speak this morning about top bar effect. Also, we can have damage around the anchoring zone if the steel concrete interface is not very good. You have the life of the crack, if it is a dead crack or a cycling crack, the cleanliness of the rebar. I deeply suspect the fact that in many countries, the salt, the chloride are on the rebar before the pouring. What are the electrochemical phenomena that happens in a crack? Is it macrocell or microcell? What is the effect of the binder, etc., etc. To precise more the subject, in blue, you have the standard life of uncracked concrete. During a very long period, you have incubation period where nothing happens, the corrosion is extremely low and not measurable. Then the aggressive agent arrived and it starts the initiation, then you have the concrete crack, you have propagation, and then you have spalling and mixed corrosion. Now, if you have a crack, it changes a little bit. These curves have been, the moment of the initiation have been thoroughly studied in the PerfDub for performance of beton concrete. But when you have a crack, the story is a little bit different. When you have a crack, first you have a very short incubation period. Then you have the initiation, corrosion start. And corrosion starts locally at a very high speed. I mean, in terms of density of current, not in terms of global current. And then you can have lots of phenomena, clogging of your cracks, and the corrosion almost stops. And after a while, the corrosion products, the aggressive products arrive by the concrete, and then you start the propagation. And so the question are, what are the parameters that govern finally this reduction of durability? Said differently, what are the governing parameters that make the difference between this story, which is a good one, and this story, which is a catastrophic one? So, A national project. So what is a national project? First, it's a French successful vessel which have been created to perform collaborative research in civil engineering. In general, it involves a large amount of contributors from many parts, public and private laboratories, university, engineering school, insurer, checker, contractor, designer, owner, etc. Budget are in the range of millions of euros, duration 4 to 5 years in order to include PhD. And the national projects are labeled by a committee. And then the IREX Institute help the project for all financial and contractual issues during the project. The project is financed mainly by the partners. So the PN name, concrete control of cracking for overdesign, it's not fully satisfacient. So it's not fully defined. We spend a lot of time to brand this national project, but it's not the major subject. What are the goals of this national project? First, investigate in details the corrosion phenomena occurring in the cracked vicinity, not in the uncracked area, but in the cracked vicinity. Identify the factors that influence the corrosion, quantify their effect, and then propose and evaluate strategy to achieve the durability at the lowest environmental and financial cost. Then after that, the idea is to disseminate the new knowledge and accelerate their implementation in international standards. These are the goals. Now the methodology. The methodology needs to stick as much as possible on existing structure behavior. And also, it must take into account the modern concrete mix design. Pure CEM1 concrete is no more used in our project. Benchmark the consistency between the laboratory results and the real structure behavior. So it's very important. Then define and test preventive and corrective action. And after that, provide recommendations for sober structural design. And to do so, I think it is absolutely necessary to involve from the beginnings international partners within this national project. So it will become an international project, but within a national project vessel. For people who know a little bit national project, you have the national project PERDUB, which is currently ending. And in this project, what was studied is the uncracked concrete, and what was studied is the ability of the concrete to provide a protection. Past project, COS.FR, concerns the prediction of crack occurrence and crack opening in massive structure. This PN aims to study what happens in the vicinity of a crack and what are the phenomena that accelerate or slow this corrosion. So the work program is based on 4 main axes: at laboratory, on existing structure, the preventive or corrective action, and the sober design and recommendation. At laboratory, the idea is to study the effect of the various parameters identified as potentially important, such as the aggressiveness of the environment, the crack width, but also the crack pattern, because the crack width is not the only variable which characterizes a crack, the quality of the steel concrete interface, the type of bender, the load pattern, etc. So the plan: create controlled crack opening, identify the cracking profile, the cracking pattern, maintain this opening over the duration of the test, and place the wall in various aggressive environments, and then measure and monitor many parameters, such like corrosion, current output, clogging, clogging materials, chemical control, etc., etc. The idea also is to propose a standardized procedure to ease the various laboratory test interpretation. And in particular, we want to classify a quintet made of concrete type, track width, steel concrete interface, and chemical environment. Because we think that these are the 5 major parameters. Then try to model in parallel to the experiment what happens in this crack by using multi-physical models. And after that, the deliverable will be standardized test procedure, experimental database, multi-physical models, and proposition to adapt sometimes exposure class toward possible subclasses in order to place the parameters of the quintet. The quintet is concrete type, track width, steel material, steel concrete interface, and chemical environment. Now, just some works have already been implemented thanks to the National Federation of Public Engineering in France. And you can see the use of two means of analysis. One is tomography. Here, the shadow is the shape of a 6mm diameter rebar. And in orange, you have the extension of the corrosion products at the crack location. And so you can measure the volume of the corroded material, of the steel which have been corroded. And so you can compare it with the measurement of the electrochemical measurement. And you can follow up very, very, very finally what happened in the crack. The axis 2 of this work program will be the following. The goal is to investigate on existing structure, which are facing in various environments, the vicinity of crack through non-destructive and also destructive tests. Exhibit a large example of cracks showing, large cracks showing good behavior, or on the other side, thin cracks showing poor behavior. And for this example, try to characterize the quintet, the aggressive compound, the corrosion product, the clogging product, the crack pattern, etc. And this will enable a benchmarking of the model. So the methodology is to first identify good candidates. You should take all structure, but not too much, because you should be still in the incubation period for a non-cracked area. Also, you should find a structure which is made with modern concrete, blended dirt like CEM1 plus fly ash plus GDBS, etc. The problem is probably to find an owner who wants to accept to make some holes. Yes, 2 minutes, sorry. So the idea is to work on structure which are destined to demolition for change of use. So the deliverable will be an existing structure survey plan, an existing structure survey report, and a benchmark report. The third program will be preventive and corrective action. So made a list of execution parameters which can be of direct influence. Use of rebar already contaminated, poor placing of the concrete segregation, excessive bleeding, etc. So define method to reproduce in laboratory sample representative of in situ defect, and then study these samples and study for this sample various various repair solutions. And the deliverable will be a proposal for technical for creating defect representative samples, relationship between concrete mix and self-healing, definition of preventive action, and supply of samples. Then after that, the last axis will be to compare the codes, compare the ability of the codes, existing codes, to take into account the result of the axis 1, 2, and 3, and quantify the interest through life cycle analysis of the various proposed strategies. In conclusion, current design rules lead to heterogeneous level of durability. Last decade code increase the achievement of the durability of the structure, but through an inflation of resource consumption, and sometimes with issue remaining. So a better knowledge of the interaction is necessary, and the natural project is a structure that is practitioner and academic collaborative work. So international experts and contributors are welcome and expected in this project, and the global structure and objective of the project are yet defined. The next step are the accreditation by the CODOR, the identification of the contributor, and then the project could start at the end of the year or at the beginning of next year. Thank you for your attention.